Good morning, good afternoon, and good evening, everyone. Welcome to our webinar series. It's under the WCRP Digital Earth webinar series on high-resolution land model and its land-atmosphere coupling. Today, it's our pleasure to have Dr. Yang Polcher to share with us this LIAISE project. So before he starts his presentations, let me briefly to introduce Yang. So Yang right now is a senior research fellow at the CNRS in Paris. And he also is the co-chair of the GWAX now. And then he also is a founder about 25 years ago for the GLASS, stands for the Global Land Atmosphere and System Studies. And then also serve as the co-chairs for WCRP and GWAX several activities. And in the past several years, he conduct this LIAISE project, try to have this high resolution modeling and also its observations, try to improve how the land surface models once we go to the kilometer scales. So it's our pleasure to have him here to talk to us about how the project's status now. So with that, I will give you the time to you, Yang, please.
Okay, thank you very much, Min-Hui. Thank you everybody for attending this webinar. So yes, I wanted to present the modeling part of the LIAISE project. The LIAISE project is quite a large European project funded by France, the UK, and Spain, essentially. And it had conducted, its main objective was to try and understand the role of irrigation onto the regional climate. And one of these activities was to try and simulate at high resolution what happens to the water cycle when we irrigate. And well, there was a field campaign carried out in 21, but we won't talk about that. So in order to try and better understand how our land surface models work at very high resolution, together with Juan Pablo Sierra and Julie Collignon, we have prepared an atmospheric forcing at kilometric resolution. And so I wanted to show what we think it is worth, and then we'll propose an experimental protocol. And finally, we have done some simulations to validate the forcing, and I will show some results of that, and which might show you how well or how badly our land surface models, one of the land surface model, Orchidée, fares at 1 kilometer resolution. So the region of interest is north and south of the Pyrenees. So we have the Ebro Valley to the south, which is quite arid, and to the north, the Adour-Garonne Valley and the Aude Valley,
Yang,
which yes.
Sorry, Yang, can you move the bar that show the view of the participants out of the yes?
No, that's too large. No, cancel.
No. Can you?
I don't know how to.
In the left one, yeah.
Okay, I'll try it. Oh no, I can make that small. Yeah, that's better, probably.
Okay, great. Okay. Thank you very much.
Great. And so it's quite interesting because the northern part is rather humid and the southern part is more arid. And so we'll see if the land surface models behave differently at kilometric resolution in these two climates. So the general strategy was to first, obviously, to use as much of the data as we have. And there are plenty of observing stations from Météo France and IMET in this area, so the two weather services from Spain and France. But that is not good enough, and especially in mountainous areas, we lack weather stations. I think the highest in the Mediterranean is around 1,500 meters or something like that. And obviously that's not good enough. So the other information we want to use is the kilometric scale simulations, which were done by regional climate models, convective permitting, during the EUCP project, which were run over the 2000 to 2009 period, forced by ERA interim. And so the idea is to bias correct these convection permitting climate models with the data and generate a forcing for the period from 1989 to 2013. As you know, hydrological processes are a bit slower, and it is important for us to sample the full internal variability of the hydrological cycle. And in that period from 89 to 2013, there were some quite severe droughts in Spain, so that's interesting to see. So the data sets we have from both weather services are in a very particular form. In fact, they're not individual stations, but rather homogeneous climatic polygons defined as such by the corresponding weather services, and the observations are averaged by altitude level on these polygons. It's quite interesting as well because it smooths out the individuality of each of the stations, which is an interesting property. And then we have the ETH and the IPSL regional climate model at 3 kilometers. And at the daily scale, we'll try to favor the Safran data. So that's what we'll bias correct with, while at the subdiurnal scale, we'll favor the RCM output in order to have consistency between clouds, rain, radiation, and temperatures. And the result should be at a 3 kilometer grid, which is regular in lat long to make life simpler for everybody. The methodology was then to take, that's in the graphic here, to take the polygons of Safran on the, you have here, then sum the 3 kilometer grid of the climate models to these polygons, compute the averages of each, get a bias, and then finally disaggregate, apply the bias to the climate models to obtain then gridded data, unbiased at daily scales. But obviously we apply this bias then to hourly data from the climate model so that we have hourly forcings. And when we transfer the bias, we can either use a bias by altitudinal class, which makes sense, but then we have some altitudes where we have very little observations, or we do an average over all an average of the bias over all altitudinal class. So these are the two methods we will explore, and that's given here. So either averaged over the entire polygon or by altitude. And as a result, so we have a correction which is temporally and spatially smoothed, and we have to ensure that the extreme values are within acceptable range, so there is a correction after that. So this gives us hourly data, which is bias corrected at the daily scale, and we can validate that with hourly data from the weather stations of Météo France, which is publicly available. So now it's not anymore on the polygons, really each station individually, and we have 651 of these sites on our region. And you also see the distribution by altitude class, where we have quite a few, obviously, between 0 and 500 meters, while above 1,000 meters, we have very few stations left, which is, well, one of the main reasons why we're using climate models in order to get this forcing. So what happens to the 2-meter air temperature? You see that the mean, obviously, over the day is quite close to zero, the mean bias, I mean, for the ETH in the first column, IPSL bias corrected with an altitudinal average, by altitude class and average over all altitude class. But you also see that the maximum value of the 2-meter day hourly air temperature is slightly underestimated by the models, and the minimum temperature slightly overestimated. And you can see at the bottom for the summer months by altitudinal class, the correspondence with the observations, so the difference to the observations. And you see that for lower altitudinal classes, we reproduce quite well the observations at the point value, but obviously when we are above 1,500 meter, then when there are observations, we are quite far away, and that is logical because there are too few observations to constrain the model. We can do the same thing for rainfall, and now also looking at the maximum values of rainfall, and you see that the mean is obviously close to zero, that's by design, and the maximum values, you see red and blue dots because there are deviation in both direction depending a little bit where the regional climate model has placed its convective systems relative to the observing station. What is interesting is to look at the diurnal cycle of precipitation, and you have in black in these polar graphics for station 1 the observation. So it rains essentially, between 17 and 20 hours. And you see that ETHZ reproduces that timing quite well, while the IPSL, which is for the atmosphere, the WRF model, is not so good. And you see also that for the station 2, which is in the mountains in the eastern Pyrenees, the maximum rainfall is between 1 and 3 o'clock in the afternoon. And the ETHZ model again reproduces that quite well, while the other one doesn't as good. So we see that the hourly data is also quite realistic in its timing of rainfall, which is obviously important for the land surface processes. And you see also the mean, let's look just at the mean difference with observations by station. So below 500 meters, the forcing is quite close to the stations. And as we go to above 1,500 meters, we do have a bias in the forcing. We have an issue with radiation. We first tried to correct the models with the ERA radiation in order to bias correct the model, and we compare it to the Clara product from UMEDSAT for long wave downward and the SARA product for short wave downward. And in fact, with by correcting with the reanalysis, we obtain, this is the second plot, the difference to Clara, some very clear error structures which don't make a lot of sense and which are probably due to the fact that ERA has some systematic spatial biases relative to the satellite product. You see that very strongly as well in the solar radiation, which is the lower graphic, where clearly in July we have errors of up to 40 watts per square meter in the mountainous areas, which is not good at all. And so we decided that we would take the satellite data as a reference and we will bias correct with this. The idea is again to compute the average fluxes from the satellite product on the polygon and by altitudinal class, and then do the bias correction on the hourly data of the model. This is the data is just ready, and I'm checking with the model that it works well, but at least this gives a much better match with the satellite products. We believe that the satellite product has in fact more high resolution information, particularly over the mountains relative to ERA, and that is much more suitable for the kilometric scale models. So now that we have a forcing, we can discuss the experimental protocol. So this forcing will be distributed publicly on the GitLab, which is partly covered, but I have another slide with the GitLab. And so we have 3 forcings we want to propose. The first one is based on the ETH regional convective permitting model with altitudinal and average biases corrected. Then one of the IPSL, so that's WRF coupled to Orchidea, also with altitudinal average of the biases, and one where we correct by altitudinal class. And then we also propose for reference one coarse resolution forcing at 0.5 degree, which is WFD5, which is a standard product we all use to test and evaluate our land surface models. So it provides over the region a reference against which we can compare. We propose that each land surface modeler configures the model as he thinks is appropriate, either with or without interactive vegetation, with anthropogenic water use, with land use, whatever you think is needed at these resolution. Try your best shot and we will compare, and then after the comparison, we'll decide if specific sensitivity simulations need to be done. For the spin-up, we propose that you run with one of the three forcings a full 1988 to 2013 simulation, and you'll use the last state in order to run your three reference simulations. So it has essentially 9 months of spin-up, as we will start the analysis only in September 89, as this is the start of the hydrological year. So that should be okay and catch up on any differences in the forcing between 2013 and 1989. The output is requested according to the ALMA convention that is standard in LSM intercomparison. And we will request the precipitation, obviously, so that we can verify evaporation and its various components, the water fluxes out of the soil reservoirs, so be it surface runoff and subsurface runoff, and the surface temperatures and the min and max during the day as well. We can rediscuss that at the end, and any proposals are welcome. So we have done a first set of simulations with Orchidee, but using the old radiation, which is not very satisfactory. The runs with the new radiation are in the machine to check the forcing. But these first runs already allow to see a few things which are interesting, I believe. So first, let's look at the catchment level water balance, because this is really the only observation we have, that is the discharge of the catchments. And we can apply this analysis to the large and small catchments in the areas, those more in the mountains or those more dominated by the valleys. And we will perform the average always over a hydrological year, so from the 1st September to the 31st of October. And we know that the sum of the precipitation minus the evaporation over the catchment should be equal to the discharge at the observation point, or the sum of surface runoff and subsurface runoff. And so we can at the same time evaluate the models, and it provides us also indication of how these catchments compare between high and low resolution. So here is the discharge simulated at various catchments. So on the left, you recognize well the catchments we have. There are 600 and something. I have written that on the previous slide. Yes, no, we have 400 discharge stations. So you have 400 catchments essentially. So on the left, we have one of the 3 kilometer simulations, and you recognize all the small catchments. And at 0.5 degree, obviously, the catchments are less visible simply because we are coarser. What is interesting is that you have along the Pyrenees, on the southern slopes of the Pyrenees, you have some catchments where we overestimate the discharge and others where we underestimate the discharge. And in this area, you would expect the model, which doesn't include anthropogenic effects, to overestimate the discharge because we don't have all the land and water usage, so all the irrigation, and also there's a bias of Orchidee, obviously. But what is quite interesting is that you can see that some of the catchments have more discharge than observed, and the neighboring catchment has too much discharge. Is it a dam? Is it irrigation on that area? These are things we need to find out. And if you compare now the bias at each of the catchments, so the model discharge minus the observed one, so the majority of catchments are above, have too much discharge, so a lack of evaporation. And you see that when you go to higher altitudes, so the x-axis is the elevation of the outflow point. So the few catchments we have with outflow points above 1,000 meters, they show too much water. So apparently, if Orchidea underestimates the evaporation, it doesn't do so in the high altitude catchment. We have to find out why. Is it either the forcing, or is it really that the precipitation is different or better represented, sorry. We'll have to see, and having many models will be helpful here. What is interesting also is that we have quite a strong contrast in the atmospheric conditions between the low-lying areas, the plains, and the mountainous area. And you have here, according to the elevation, binned, so each grid box is binned along its elevation. And you have in full lines the precipitation. So you see that WFDE5, so the coarse forcing, has a little bit more evaporation in the plains. And then as we go into the mountains, and especially above 1,000 meters, the high resolution forcing produces much more rainfall, or provides much more rainfall to the land surface model, with a large difference between the two high resolution forcings. And at the same time, the potential evaporation, so the atmospheric demand of the atmosphere, is highest in the plains, which makes sense. It's a little bit lower in the high resolution forcing, and it decreases as we go into the mountains. That makes sense as well, because it's colder and there's less radiation in the mountains. And so that means that in the mountains, you have areas where there's in fact more rainfall than evaporative demand. So typically a humid catchment where we'll generate a lot of runoff, which is going to go down into the valley, where it can feed evaporation. So if we represent correctly the hydrological processes, the lack of precipitation in the valleys in our high resolution forcing could be compensated by the flow of water from the mountains into the valley. This is something we have to see if some of the models are able to simulate that. If we characterize in the Boutique diagram, for those who don't know, it is on the x-axis the aridity of the catchment, and on the y-axis the evaporation efficiency. So on the x-axis we have only a climatic forcing condition, while on the y-axis is the evaporation. You see that, so sorry, for the aridity index below 1, we are in humid conditions, and as we go to higher values, we are in arid conditions. You see that the low resolution forcing is quite close to the high resolution forcing for all catchments which are below 2 in potential evaporation divided by precipitation. And as we go to more and more arid catchments, in fact, the high resolution forcing produces less evaporation or a higher aridity. And that is quite interesting, because this could be the result of the fact that Orchidea doesn't include lateral transfer. So the low-lying arid catchments are not fed by enough inflow from the mountains. This is something to be determined. Another analysis we have done is to look at the temporal variability, so day-to-day variability of surface temperature. And that is something where we have Meteosat-derived products. So you have on the leftmost column the variance of the surface temperature anomalies for the month of not July, it's all of summer, from May to August. So you see that the surface temperature variability is low close to the sea, simply because it is cooled by the sea breeze. And as you go inland, as you go to more arid conditions, so that is the southeastern part of the domain, in fact, you have day-to-day variances of surface temperatures of around 4 degrees. Okay, and this is reproduced relatively well by the model for both forcings, so ETH and IPSL, with some strange behaviors in the mountains. This is something we hope will be solved by the new forcing. If we compare the day-to-day variance as well of the 2-meter temperature, in the left column you have EOPS, temperature and humidity, and you see that it's quite similar, with a larger variability for our forcing in the temperature, and the moisture is very similar. So apparently there are things which are correct in the day-to-day variance of the surface and near surface conditions of the model. But what you can already see for the surface temperature is that there are some features in the observation, like here where my arrow is a little green area. And also you have impression that along the blue lines, which are rivers, you have less variability of the surface temperature than in the model. And if we superpose on this, now the meteosat is down here. So in orange, purple, you have the delineation of irrigated zones. You see that we have minimas of surface temperature variability in the irrigated areas of around 2.5 and 3 degrees, while the model doesn't capture that at all. It has surface temperature variability of higher than 3 degrees. So clearly, there are features in the observations which are not reproduced by the orchidea at 3 kilometers. And obviously, at 0.5 degree, we do not capture at all that high variability of surface temperature. So clearly, the high resolution forcing brings something to the land surface model. For comparison, I've added here the Google map where you clearly see regions of high vegetation along the valleys. You see directly where the rivers are on the map, and you see a minimum of variability in the meteosat image, but you don't see it in the model. So clearly there is an issue here. If we look at the similar diagnostic, but now over the northern part of the domain, so the Landes here in southern France, you see that the model and the meteosat image are much closer to each other in terms of spatial distribution of the variance of surface temperature. And there is not a big difference at 0.5 degrees. So clearly in the northern part where there's much more moisture available, the high resolution doesn't play that much of an importance in the surface energy balance, which determines the surface temperature. So we are more in an energy driven regime where the resolution is not that important, while in the southeastern domain, the surface balance is more driven by water availability, which is obviously highly dependent on the resolution. So that is quite interesting to have these two aspects and be able to see if all models agree with this diagnostic or not. So the preliminary analysis has opened a lot of questions we hope to answer as a community. And in particular, the issues we have identified in Orchidea, are they particular to our models or do they show up everywhere? I think with this first analysis, we've also shown that the forcing is quite credible at its resolution, because it's easy to interpolate to a higher resolution, but it's more difficult to add pertinent information. And I think we have shown that. And how does the fact that we're missing some processes affect the hydrology of some of the catchments? That's an open question. Do our models represent properly the surface temperature and its or diurnal variability? Are there processes, or does that diagnostic allow us to identify missing processes? That's interesting, an interesting question. And are these processes either water management or hill slope processes? And that will need to be explained and explored with the various models. So I believe that running our land surface models with this forcing allows us to see how valid and applicable they are when they will be coupled to kilometric scale models. So we can identify the errors they will probably generate once they're coupled. And the more models we are to participate, the more robust our diagnostic will be of the developments we need to do in order to have better kilometric scale land surface models. So if you want to participate in this intercomparison, please send me an email with your models and perhaps already if you have ideas on how you will configure it. We'll keep you informed on the progress. I hope that next week we can release the full forcing and that we're verified that it works well. and you can monitor our activities on the GitLab, which is given here. Thank you very much, and I see that there are already questions.
Well, great. Thanks, Yang, to introduce this project and also share with those interesting results that you found from the Orchid model. And then, yes, you already clicked the Q&A box.
Yes.
So what?
So I
Okay,
can
can you
answer
answer
to
it?
Craig directly. Hi, Craig. Yes, we would have loved to have the forcing until 2021. But the issue is that the Safran data over Spain only goes to 2013. And the organization in charge of continuing that effort doesn't have the resources to continue to prolong it to 2021. That's the issue, essentially.
Okay.
So,
But in the future, did you or your team want to extend the data?
yes, we'll have to see how. Yes, if we
I see.
can
Okay,
if we can find a means to do that, that would be wonderful.
gotcha. Okay, and Fuxing,
Yeah,
and I think
Fuxing. Hi,
you.
Fuxing. Nice to see you. No, there's no groundwater transport in Orchidea at the moment, and the urban parameterization was not used either. So there are two large cities in that domain, which is Barcelona and Toulouse. And we haven't looked in detail, but that is a good question. And possibly those models which have an urban model should try that and verify over these cities. Toulouse is wetter than obviously the southern part of the domain. It is far from the sea, so that's good. Barcelona will be strongly influenced by the sea breeze effect, so I don't know if they are really representative of not or not, but we'll see.
Yang, may I follow the question
Yes,
about the groundwaters that? So I thought that there's a groundwater version in Orchidea.
yes,
So
we route the surface water, but we don't
yes,
yet transport the groundwater from grid to
I
grid.
see.
So this is something I want to test with this setup. And
Mm-hmm,
I have the impression that we see that the hill slope groundwater is missing in Orchidea. But
mm-hmm. Yeah,
we have to, well, it has to be quantified, and then once we add it to the model, we have to see if it really solves the problem or not.
I see. And and there's a question from the chat box. Can you see it?
No, I don't
I,
see.
yeah, you can click on the chat box.
Wait, I
Not that
don't have a
one.
chat. Yeah, Craig has. Yes,
Well,
Orchidea
no, this
has
is
participated in Plumber 2 and Bob. Which of the Plumber flux sites could be in the domain? Excellent question, Craig. I don't know.
so how many? Oh, okay. So there are the Sprux next side. No, Sprux sites.
Sorry?
No, that's can you open the chat
Yes,
box?
the chat. Yes.
Okay.
What? No. Where is it?
Oh yeah, not this one.
Or can you read to me and then
Yes, I can read for you. Okay, so from Rita that can you put the ELAB address in the chat, please? But I think I will do that later. And what's the depth of your soil labels?
Sorry, I didn't understand that.
What is the depth of your of the Orchidea soil
Yes, in
labels?
Orchidea it's 2 meters. Well, I have configured it to 2 meters, but
Okay, so
yeah.
2 meters.
Yeah.
I see. And what else? Hold on. And from Promit, there's another question about, is this a process-based model? How's the primary productivity models here? How's the GPP simulations here?
Yes, that
Did,
is.
did you?
No, we didn't look
Yes.
at it. And this is a question also. So let me step back. Yes, the dynamics of the vegetation, in particular the GPP, is an interesting phenomenon because obviously in the arid areas, if we don't have rivers or groundwater bringing water to the plants, you will have less GPP than what you would observe. And this is something we can perhaps check with NDVI products if we do the LAI in the right areas of the region. The issue a little bit here with this region is that obviously the LAI is not natural in any way, so it's all driven by agricultural practices. And this has to be seen. Either we believe that our models can also do manage crops realistically, so then there's a point in validating, and if not, then obviously it's a bit more complicated.
I see.
Related to that is also the question of output variables we will collect. For the moment, on the wiki, you will find a list of variables we have requests or we want to request from the participating group. If there is a strong interest in biospheric processes, then we probably need to add a number of variables. And now is the right time to do it. So send me an email and we can then extend the list of variables.
I see. Great. And I think, Yang, can you move the toolbox that in your button to up? Can you see whether there's a checkbox? No.
No, I don't see. I have here a chat, but it doesn't. Or is it
Even
behind
sure?
my screen? No, it's not behind my screen. I don't know where it is.
Maybe you can stop sharing your screen and see whether you can see the checkbox or
That's
not.
yes, that's also. Now I have.
Do you see?
Yes, now I
No?
have something. That's better.
Okay. Okay.
Good. Where do we stand?
And I think Ashish also post the question on the Q&A, so you can take a look at the Q&A.
You want to test the forcing? No. So the convective permitting regional climate models were run driven by ERA interim. So they follow as they can the large-scale synoptic variability, but obviously being convective permitting, they will place the convective systems in slightly different locations than observed or done by the reanalysis. So it's not, yeah, you have to pay a bit more attention when you want to validate very spatially variable fields.
Yes.
So yes,
I see. Well, thanks, Ashish. Thanks for the question. And okay. And Yang, I have a related question. So when you use the high resolution coming model to generate these forcings, then as for the temperature, do you use the lowest the atmosphere model's lowest level as the temperature to drive the lenses model, or
no,
you
the
do the
forcing.
interpolation?
No, the forcing data is 2-meter temperature and 2-meter humidity.
Yes, but that's from the convection permitting models.
Yes, but it is
Uh,
also, it is bias corrected with the observations at 2 meters.
I see.
And the wind, I believe, is at 10 meters.
Okay.
But that is pretty classical for land surface models when they're run offline.
Yeah, if in a coupled model, that the lenses model will use the lowest button, it's
Yes,
called T
sure,
button or Q
sure, sure,
button,
sure,
then do this
sure.
interpolation. Yeah.
No, we don't. Well, you don't interpolate, but you get other
Mm.
diffusion coefficients because you have
Yes.
your function of ln of k divided by z over z naught. So that scales directly.
Yes. Okay. Cool. Do we have any other questions? So do you have any timeline for, because right now if other peoples want to join and run the different lenses models,
Yes.
and any timeline for that that you have now?
I expect that next week we'll be able to distribute the 3 forcing data sets. We will also distribute those with the radiation corrected by the reanalysis, which is not very nice, but we can distribute it. It doesn't. So if somebody wants to do a sensitivity analysis, something like that,
Mm-hmm.
and as soon as the data is out, would be nice if we could have the model outputs in January or February, because it's not that big a domain, so the model runs quite quickly.
I see.
Last week, I was at an ESA meeting, and the hydrologists also have a kilometer scale forcing. And because the hydrologists have explicit representation of groundwater and so on, I was thinking that it might
Oh.
be interesting to use also their forcing so that they participate with their models, so that we compare land surface models and hydrological models. That could be an idea. I'm not convinced that their kilometric scale forcing is as good, but well, we never know. We can compare and see what it gives.
I see. So do they run at the same domain as well, or other regions?
They run over all of Europe.
I see.
But if anybody else has a high resolution forcing which they think is good, then we could add it. The more forcings we have, the easier it will be to separate the forcing error from the model error.
Mm. So those forcings that you provide is 3 different models. So, but no like ensemble ideas to perturb the initial conditions that's done by each groups. If we want to do the ensemble simulations, so we just do by ourselves to perturb the initial condition, or
Yes.
any thought about it?
Not specifically, but I think the models will very quickly rejoin
The forcing.
the forcing. Yes, yes, yes.
Yeah. Since some of the grid cells that you in this project are kind of relatively dry,
Yes.
so that may take some time to spin up,
Yes.
although
That's
we already have 1 cycle.
exactly.
Yeah.
But you see, really, there's relatively when you're working at 3 kilometer, the real observations you have available are few. So you have
Mm.
so for instance, everything which is above 1,500 meter is invented. There is no observation. And that
Mm-hmm.
is where the most part of the rainfall falls. So any other estimate of the forcing at these on these non-observed areas will be interesting.
I see. Yes. Yeah, that's true. And actually has another question about the TS and T2M. Can you check the Q&A? Yang, can you check the Q&A box?
Who put that question?
In the Q&A box.
Yeah, but
Okay.
which question? Because the last one I see, no, the Q&A box now. It's a different one. I'm perturbed. It's too complicated for me.
Yeah, it's basically
yes,
the
now I have
question
one.
is about. Okay, great.
How good is TS? And so Meteosat doesn't observe 2-meter temperature, 2-meter humidity. So that's bad. From Meteosat or from satellites, we only have surface temperatures. And the 2-meter temperature, we could compare it to, well, we have compared it to the stations, which we have available in France. We could compare it to reanalysis, but reanalysis is at best 25 kilometers. So there is a European 5-kilometer reanalysis we could check, but it's also just a model at these resolutions.
I see.
So it's a bit of a challenge to provide forcings at 3-kilometer resolution, even over a well-observed area of the world.
Okay. Yeah. Okay. Cool. And Craig just mentioned about this singular event. I think yes. I want to mention to everyone that focus on the high resolution the model, and then atmosphere coupling will be bi-monthly. So the next one will be early February, and we will arrange it and announce it probably sometime January. Thanks. And yeah, everyone is welcome to join. And if everyone want to share your research topic on this high resolution model, please let me know. I will help arrange the timing as well.
Perhaps by then, in 2 months, we can provide a table at least of how many groups want to participate or have already provided runs.
A good idea.
Okay,
yes.
So we can keep people informed of how we progress with this community effort.
Great. Yeah, sure, definitely. It's a good idea. We can and let me know. I can share in the beginning of the webinar in February.